So good evening, participants. We will move into today's second session. So second session is handled by Dr. Jekin Winston. He is the research scholar of Dr. Jude Heyman. He is now serving as an assistant professor in Division of Electronics and Communication Engineering at Karna Institute of Technology and Sciences. His research and teaching interest encompasses optimization methods, deep learning, biomedical image analysis, interactive intelligence systems, DSP, machine learning, computer vision, IoT, AI, and array signal processing. He has more than 30 journal conference publications. He is a member of IEEE. And in this session, he will show a hands-on session how to integrate AI with antenna design. So warm welcome to Dr. Jenkins, sir. So I'll hand over the session to him. Participants, if you have any queries in between, you can put the questions in the chat box. Thank you. Thank you for your active participation. We welcome you, sir.
Thank you so much, ma'am, for your kind introduction. Let me share my screen.
A screen is visible, sir.
Yes, ma'am. Thank you for your response, ma'am. Before I start, I would like to thank Jude Heyman, sir, for his mentorship and guidance over the past several years, which has developed my interest and my skill sets with respect to AI and image processing fields. And he has put up enormous trust besides so much of failures, and that too I admire as a mentor from him. Thank you, sir, and also thank the organizers for putting me into Dr. Shinelet ma'am and Dr. Nesuda ma'am for great for inviting me for handling this session. And I'm joining from here. This is our university, the aerial view of our university. I'm joining from this place. Over to you for this session. And how we are going to proceed for this today's talk is a little bit of introduction about the antenna, and we'll try to take it up how ML is related, and from there I'll try to take it up into an EM simulator where a small patch antenna is designed, and later we'll see how we can try to extract and make a data set which could be viable and integratable into a machine learning code. And if time permits, we'll see a neural network or a machine learning model simulation, and then further we'll see about the optimization part. And this is about the session. Half an hour we'll have a presentation, and half an hour with the EM simulator, and then the half an hour with the Collab platform. So we'll see, and we'll go ahead. I hope you can grab some coffee in between and sit with our time till we start up with some hands-on. As we formally announced with the start with this session. As you know, antenna is a form of a transducer capable of translating one form of energy into the other. So the guided electrical energy being getting into a free space, and vice versa. It can also be thought about as an impedance matching network. Okay, so between the transmission line and the free space. So the free space impedance is said to be around 377 ohms, and maximum power transfer happens when the antenna matches with it. And yeah, these are the basic ideologies which would have discussed, or which you could have come across in textbooks, the formal introduction how antenna is. Okay, and you would have also seen a wide range of applications where this is used, starting from maybe primarily it started up with telecommunication. Okay, your broadband communication. Now we use it in the field of military for radar sensing, and in 5G communications. Even we have gone into the form of taking this antennas into medical field also. So as we said, the any technology which comes, okay, that can have a wide, broad area of application. So to begin again with the characteristics of the antenna. Okay, basic antenna, what does that usually we actually see in an antenna is, first it should have a high gain for it to be used in a particular application. So what is this antenna element which will actually help in trying to enhance this gain? As you can see, you can try to increase the number of elements, okay, forming it as an array, or you can try putting up a parasitic patch element, okay, to improve this gain. And if you see about the next important characteristic of an antenna is wide band width. Okay, you can see this ultra wideband applications in a quite a wide form of applications like telecommunication applications. For this to happen, the important element which is used is putting up a slot, or having a partial ground, or having a parasitic patch, okay, or having a substrate with low permittivity and increased thickness. So these are the things you can try with introducing into your structure to gain this wide bandwidth. Now, why do I start with this? You may think, why should I start with this kind of notion while we had to discuss with dataset preparation? The idea I wanted to bring is there is something called design parameters. Okay, so the design parameters, you can directly go and design with a mathematical equation. But what fits in for that particular application, that is also most important to understand. So once I list down all these things, basically you can try to map it out what kind of methodology or what kind of element I can choose for increasing for your respective fields. And certain applications require circular polarization, and that can be achieved with this truncation and going up with orthogonal feeds. And the other one is the miniaturization. You could have come across this meander or folded patch structures that is helpful in miniaturizing your antenna structures. You can go with high dielectric substrates and slotted patches as well. And then frequency reconfiguration. As the webinar, as the FTP program is also more related with this topic, you know this concept is achieved with the help of integration of pin diodes and switchable stub feeds. You would be able to achieve. And then radiation pattern control. The preliminary usual Yagi-Uda antenna, you can see how this directors and reflectors are help in controlling the direction of the radiation patterns. And if you want to have multi-band applications, you can go with introducing multiple slots and combination of patches with different sizes. And for impedance matching, the usual approach in POSAR book, if you see, you can see that about insert feed, water wave transformers, okay, and the other probe feeds you can use. And for MIMO applications, basically they go with defected ground structures and parasitic decoupling structures. And for beam steering, you can see some phase shifters with different patch elements individually driven with different phases. You can achieve coherence of those beams in having highly tensile beam directed to a particular directions. So this is the essence how you can or the recipe with which you can try to build up a good antenna which you want for the applications which you have said, be it radar, be it for an aeroplane, be it for an automotive, or be it for an access point or a Wi-Fi access point you want to think, okay, or a medical healthcare. We can try to integrate all these kind of things with the help of this different enhancing antenna element. Now, what is the objective? What is the ML model here going to do, or what is it trying to predict here? ML model is, there are three different categories how you can use ML model. The first one is the forward modeling. So in forward modeling, the input which we give to the ML model is the antenna parameters. So what could be the antenna parameters? As we said, the dimensions, the geometry, it could be a circular or a different shapes which you have, the materials which you have. So all those things are the input parameters. So once you take up all these input parameters and give it to the ML model, it will tell you for this antenna which you have made using this dimension and this material and this geometry, the expected performance metric of the return loss or a gain or a bandwidth or pattern radiation expected is this. Okay, so why do we have to go for this model? Again, I'll go into a little bit discussion from this further also. Okay, so first is an ML model. You're given an input and you try to expect a certain output which would be good in modeling your antennas further. And the next one is the inverse design. So here exactly the opposite of the forward modeling. So for the input you're given, this is the S11 I want, or this is the gain I want for my antenna. This is the bandwidth I need. Can you suggest me what is the antenna I should go for? What is the dimension I have to choose? What is the material I have to take? Okay. So for this purpose also, we can try to use ML models. Okay. So try to have this curiosity, how and all we can try to use a basic ML model. Okay. And the next one is surrogate modeling. Okay. You can either use way of forward modeling as well as inverse modeling. Okay. So in surrogate modeling, what do we mean is, you know, the surrogate mother who is actually getting conceived. You given the baby, and after 9 months, she can deliver the fully grown offspring. Okay. Similarly, once you have a good ML model, okay, once you're trained up for a particular iterations, the ML model is fully trained, then it is actually called as a surrogate model. That model can be used, okay, for predicting certain outputs. Okay, given this inputs, what could be the output? So that is the concept of surrogate modeling, and this surrogate modeling is widely used in machine learning field in the applications of antenna designing. So to start with the overall framework, how this modeling is being used is, first you come up with the idea. Okay, what is my design? What is my specifications? Okay, what is the frequency I want to operate? Okay, what is the size I want to have? What is the geometry structure? That is all put up. Okay, this comes from the first slide which I showed, where antenna characteristic and its neighboring element which can aid in improving that particular characteristic. So with that, you can make up a overall blueprint. So you have got a design now. Okay. So from that, what we go. So once you have put up a intuition from the literature, you have found up some structure. You go into the EM simulation tool. Okay, and you design that particular antenna. After that, you take up that simulation. Okay, you got the parameters. Okay, so these are the dimensions from the equations you would have solved. Okay, take it up into the MATLAB tool or CST or ADS or any kind of an EM simulator. Okay, you can go into there and you can try to simulate how your antenna responds. This is the usual procedure of antenna methodology. Okay, antenna simulation. So what you get, you try to find out what is the output. So what would be the output? You would get something like a radiation pattern. You would get gain. Okay, you would be getting a S11. Okay, so these are the outputs. Okay, you have desired. Okay, in the first stage. So after simulating in the EM tool, you're seeing whether it is coming or not. Okay, with the graphs which are extracted. So if not, what will you do? You go back again into the first stage, design template. You will go into the design template, try to vary some parameters, go into the simulation tool, and again you see whether the result has been achieved. So this is how you usually design. Now, how do we try to use this even more simplified without going into much into the EM simulation and achieving the better results? So for this, with the results which you get from the simulator, you can try to develop a data set. Okay, so where you all the inputs which are given for the ML model, we call those as features, and the outputs which we get, we can call them as targets, or you can also call them as labels. So given the features into the ML model, we are trying to train that it actually tries to find out the label for it or the target for it. Okay, so once that is there, okay, data set is there. Okay, you can go and train your ML model. You can choose any of the ML models, be it support vector regression, okay, XGBoost, multiple layer perceptrons, or back propagation networks, or CNN. Okay, you can try to take up multiple ML models. Okay, and then you can try to achieve whether that is there. Okay, so once you evaluate the results, okay, you see that is not perfectly trained, and you go train it back, train back the model again. So you try to do this in an iterative phase. Once that is done, and you have got the fully trained surrogate model now for further process. So this is the final, this is the idea into which we are going to work on for this session. So first we try to take a patch antenna, try to put it into an EM simulation, extract the data set, go into training a surrogate model, and try to find out what is our model performance. Okay, and if the time permits, we will go further with predicting outputs with that model, and then try to revise this model again. Okay, sometimes the surrogate model, even if it is trained, okay, we can go for finding out what is the best, maybe the length of the patch, width of the patch, or the length of the feed, okay, which could be optimal for my design. So for this, you can try to make use of evolutionary algorithm. So this evolutionary algorithm has a objective function. So the objective would be to improve the gain of the antenna which is designed, okay, within that frequency band. So you can have constraints, you can also have objectives. Okay, so in this band, I want to achieve maximum gain. So what should be the length and what should be the width for this? So I can try to take up any algorithms like evolutionary algorithms like GA or TSO or ant colony, or so many optimization methods are there. You can try to adapt any one of those things and try to use them and try to find out what is the correct value with the surrogate models. At last, you will get the final design, the best length and width for this particular structure as this one. Okay, so as every design goes, okay, we start with the patch design formula. You can go into this website, pasternak.com. Okay, I'm going to fix up with a 2.4 gigahertz frequency patch antenna. So we'll try to find out what is the width, length. Okay, epsilon R, I will try to take it as 4.4, which you use it for an epoxy, FR4 epoxy substrate. Okay, and from that we can calculate, you know, C is the velocity of light. Okay, so your observations, your calculations, you can directly go into this calculator and find out what would be the width, length. Okay, so how are we going to augment into this HFSS model is the first stage is we are going to create the ground, okay, the substrate, the patch. Okay, I'm going to have an insert feed. So patch is there, the insert portion is there, the feed line is there. So combining first the patch with the insert, you will be getting this structure. Okay, and then fusing the feed line with the subtractor structure. Okay, we would be getting a final structure like this. Okay, so my objective here is to use an ML model. What should be my LP, and what should be my WP, and what should be my LI. Okay, what is LP? LP denotes here the length of the patch, WP denotes here the width of the patch, and LI denotes the length of the insert section. Okay, so these are the three things which I want to find out optimally for my patch antenna. Okay, on doing so, I'll try to find out what is the best suitable structure which is there in the stage 3. Okay, I want to finally come up with that particular structure. So for creating data set, I need a base model. So I try to create 9 different base models here. Okay, so you can try to just find out what I have done here. I've tried to take up 3 frequency bands. Why have I taken this is, even if I try to stick on with 2.4 gigahertz, okay, once I go into the simulation mode, the model sometimes behaves to be, more resonating at some other frequency. Let's say it would go above 2.4 or it would come below 2.4. So I wanted to just try to have how the antenna behaves. Okay, so for that I've taken up different frequencies as my design, and I'm going to develop my models in HFSS. So for 2.4 gigahertz, the length of the patch and the width of the patch from the equations we have got is 29.4 and 38 mm. So for this structure, I'm going to have 3 different feed length. Okay, one is 0.5 times half of patch length, and 0.6 times half of patch length, and 0.7 times half of patch length. So for the first frequency, I would be getting 3 base models. Okay, I'm going to extract the S11 value out of the base model. Okay, and then for the frequency 2.5 gigahertz, I'm going to generate another 3 base models, and I have to generate my extract my S11 for the from the model. Okay, and then for the 2.6 gigahertz, I have found out what is LPWP. I varied the insert length positions for 3 things, 3 different locations, and then I've got out again. I'm going to take out 3 different models. Okay, so how will I be able to do this in another half an hour? I'll do my best. Okay, and I'll try to implement all these things, extract this, and make a data set ready for training an ML model. Okay, so
what is the meaning of base model, sir?
So base model is the first precise model on which I'm going to extract my data set. The base model would be not the final design. It would be an abstract model. Okay, as I said, the stage 3 is there, right? So the stage 3 is what I'm trying to develop. Okay, so for this, the dimensions would be different. Okay, for the first base model, the dimension would be L and W would be taken from 2.4 gigahertz. Have I answered you?
Yes, sir. Yes, sir. Thank you, sir.
Yeah. So I'll try to take up all these 9 different models. Okay. Maybe I'll be real quick because this is little preliminary, as you would have done in several stages of learning sessions you would have attended. So once we have done all these 9 models, I would be having 9 different data. Okay, all the 9 different data I have to combine into a single data set. So once I do with that, combine all the data set into a single data set, I will do some rectification process suitable for training the ML models, and then we'll go into a collab environment where we can put that into that ML model and do some simulations of building a surrogate model. So how do we do first? Okay, you build and you go into an EM simulator, try to build this structure, Okay, and I've put up some notations here. Okay, so these are the entities which are going to be there in the model, starting with ground plane, then we go with the substrate, and then ground plane is a two-dimensional. I'm having this dimension variables as LG, WG. Okay, and then their position variables also I've given. If you want, you can try to take a screenshot of this, and then you can follow up the procedures what we are trying to replicate, and then build a three-dimensional substrate. Okay, so length of the substrate, width of the substrate, and height of the substrate. Then go with building the patch, and then we'll have an insert section, feed line section, build a radiation boundary, go and give the ports. Okay, and then we are we're almost ready to build our first base model. So once I do all these things, I have to go for subtraction and combining all those patch, feed, and insert sections. Okay, and I'll be able to create my first base model. So after doing that, so once I go into this, so first, how should we actually approach when we try to do this kind of modeling is, generally you have an equation. Okay, so first you go with the design. Okay, so for the design parameters, okay, first we have to go with, because we are going to create 9 models. So if you are going to do it with very quickness, you can better give the dimensions in the form of variables. So I have to go and to the HFSS and go design properties, go give all this as a variables. Okay, you can see LG, I'm going to give in here the values. WG, I'll give the values. The length of the substrate is equal to length of the ground plane. So LS, LG. Okay, then width of the substrate is equal to width of the ground plane. So you know the ground is set, substrate is set. Okay, and about that patch is there. So patch was calculated from the resonance frequency. So for that LP and WP, any EM calculator you go, you can give in that frequency. You can see that is coming as 28.2 and 36.4. Okay, I've given the same value into this particular thing. Okay, and then the feed length is half of the ground length. Okay, ground plane's length. Okay, and then width is usual width of any strip line. We try to have it as 3 mm. Okay, a 50 ohm characteristic impedance. For that purpose, we'll try to use that. Okay, and then the insert feeds length and width is given here. So initially, I'm taking 0.5 times LP by L2. Okay, so I hope you can try to yeah. So this is the point I'm saying. So you have, these are the variables LF, LP, WP, and then this LI. So once you have set this radiation boundaries, you can give them all these things. So first, if you have made up with this model, then we can very well fast forward and go. Okay. So this, I think you would have heard in the sessions how to assign radiation boundary, how to assign ports, how to assign material properties. Okay, for your models. And then for extracting results, so you assign frequencies. Okay, going to the project manager, do the initial settings, and then going to project manager results and try to get your graph plots. So at last, I should be able to extract something like this. Okay, so data set, I would be able to extract something in a .csv file format with their frequencies, patch length, width, okay, insert length, and their corresponding S11 values. Okay, so this is the data set I want to prepare. The first column indicates my model number. Okay, so this is the first model numbers. From 2 gigahertz to 3 gigahertz, I would have populated my values and I've made it into an Excel file. Okay, so this is one part of the data set preparation. Okay, so now ML regression models, as I said, my output is not something to be classified. It is a number to be predicted. What should I predict? The length of the length of the patch or width of the patch, okay, or the insert length, okay, or I should predict what is the S11 for this model, okay. So something like a numerical value. So these kind of numerical predictions we will use with the help of regression models, okay. So the inputs which are given, that we call it as features, and the output, that is target, okay. The function which is actually mapping, okay, the input features with the target is going to be your ML model. Once you try to map this, there is not going to be a perfect fit between the input and the output, okay. There would be some randomness in this thing. So this kind of thing differs from model to model. Once you choose a better model, you would be able to better try to take, but that depends upon the complexity of the structure we have, okay. So some examples of models which you can think about: linear models, tree-based models, okay, advanced models like support vector regression, KNN, and deep learning models like LSTM, CNN, deep belief networks, okay, and regression neural networks. So I'm going to build a ML model now, okay. For this session, we are going to build an ML model with XGBoost and AdaBoost regression, okay. So with these two regression models, we will see, given a set of L, W, Li, and F naught, okay, what is going to be my return loss and gain, okay. I think I'll stick with the return loss alone, okay, because for another 1 hour, we should be able to complete the simulation also. Okay, so once you build a model, okay, so you should be able to find out, is the model completely able to understand how my antenna is exactly behaving for the dimensions, okay. So how do we evaluate that? Okay, so with the help of some metrics, okay, like mean square logarithmic error, okay, root mean square logarithmic error, variance, and this is called R square also in literature. This is the widely used evaluation metric in solving any kind of ML models. Okay, so R square value, if you are 1, then it is a perfect fit, or close to 1, 0.9 and above. Okay, if you have a value for your ML model, then that is going to be a very good ML model to work on. Okay, the other metrics like mean absolute error, mean absolute percentage error, mean square error, root mean square error, these are also other metrics which you can use how well your model has been trained, and that could be used as a surrogate model. You can give a certified, right, my error metrics, my model is behaving well, go ahead further and use it as a surrogate model. Okay, so okay, so before we go into this next presentation, we'll start with the simulation part. So my objective, as I said, we will go with simulating in an HFSS environment, okay, and then we'll try to build the data set first. So for this, what should I try to take up here from here? Okay, so yeah, so I've opened up an HFSS window. Okay, so first I'll go ahead, open this HFSS. Okay, so from now on, mostly try to follow the screen which I'm sharing. Okay, maybe very few I would be saying. Okay, so for I'm trying to have a create a model. Okay, so for this, first what we have said is we have to go ahead first and create my design metrics. So how do you bring this design metrics also into this picture? So first the ground plane will finish first. Okay, so I'm going to fix it as 60. And then the width of the ground plane, I'm going to fix it as 60 mm. Okay, and then comes the substrate. Okay, length LS. Okay, and that is going to be equal to the ground plane. Okay, and then the width of the substrate, and that is going to be equivalent to the width of
Excuse me,
the,
sir.
yeah.
Sir, it is not visible, sir. The boxes are not visible.
All right, all right. Then I think I have to share my whole screen.
Yeah, it's like a plain screen, sir, white screen.
Is it visible now? Is my screen visible now?
Yes, sir. Yes, sir.
Yeah. Okay. Thank you for the response. And then I have created my given my LG, that is ground's length and width as 60 mm and 60 mm, and I've started up with giving my length of the substrate equal to the length of the ground. I'm going to give width of my substrate equivalent to the width of the ground. Okay. So this is done. Then coming to the patch. So length of the patch, it should be, what should be the length? As we have already put up here, I'll try to take it up from here. So 29.4 and 38. So 29.4. This is for 2.4 gigahertz. I'm first fixing up my base model. So this is done. Okay. And then I'm going to take up my width of the patch. So 38. Okay, so this is done. Next, I think height of the substrate I have missed. I will give that HS. You can choose that as 1.6 mm. Okay, so done. So next is after this substrate, I have to go for the insert section. Before that feed line, I'll try to fix. So length of the feed is going to be okay, length of the feed is going to be substrate length by 2. Okay, and the width of this feed, I'm going to fix it like 3 mm. Okay, so this is done. Okay, and then I'm going to take up the insert section LI. So LI is actually the length of the substrate is going to be. So here I'm trying to take it up from here. Okay, so I've given half of the patch minus this one. Okay, so okay, maybe I'll give like this 0.5 times LP by 2. Okay, so this is the first length I'm going to work on. Okay, and then the width of the thing is width of the feed line plus 2 mm for my 1 mm on the left side and one other 1 mm on the right side of the feed line. Okay, so this is the width and length of the insert section I've put. Okay, so what else is there? Okay, so I have to go for the decision boundaries, radiation boundaries. So the length of the radiation boundary, I'm going to fix it like 80 mm. Okay, and the width of the decision boundary is also, I'm going to fix it like 80 mm. Okay, and then height of the radiation boundary, I'm fixing it like 40 mm. Okay, okay, so this is done. Okay, so I go ahead first, put my patch. Okay, so so this is going to be my ground. Okay, and ground plane, and I'm giving it some color. Okay, so this is done. So above this, okay, I have to give the dimensions also. So minus LG by 2. That is the starting point where I'm going to start. Minus WG by 2 and comma 0. And the dimensions is going to be length of the ground and width of the ground. So once you give that first, this becomes easier, because later when we have to change our model, you can directly change the variables. Your model would be easily extracted. So apply this. Okay, you would have got this done. Okay, then go ahead, take up this 3D box and create a okay, so this is done. So let me go for this box. Okay, so for this, the dimension is L substrate, right? So LS by 2, comma, minus width of the substrate by 2, comma, 0. Okay, and length of the substrate is LS, and width of the substrate is WS, and the height is HS. So we are done with the substrate now. Okay, so next is giving up a patch. So I go ahead and give this patch. So this patch is okay. So here it is. So this is going to be my patch. I can choose a different color for this to differentiate in the later section. So once that is done, go and give the position of those things. So patches LP and WP. So starting point is minus LP by 2, comma, minus WP by 2, comma, HS. Okay, and this is LP, and width is going to be WP. Okay, so applied, click OK. So this is done. Next, I have to go ahead and find out and put a insert section for this. Okay, so for this insert section, give a variable so that I can later differentiate. Okay, so apply, click OK. So this is done. So for this also, for the insert section also, I think we have to put the positions correctly. So this position, this is LP by 2 minus LI, comma, okay, and minus WI by 2, comma, HS. Okay, so this is the starting position, and this is going to be LI, and this is going to be WI. So our insert section is also prepared. Okay, next is having a feed line for this. So I'll go ahead and put my feed line. So to start with, give the name feed line. Click on OK, apply. Okay, and go and fix their positions. Initial positions we have to fix. So feed line has been taught. So this one I have to position where it is going to start with. So it's going to start from 0, comma, minus WF by 2, comma, HS. Okay, and the width and length is going to be LF. Okay, this is my feed line, right? So WF. So apply and get set. So we have done with this. Next, what else are we expected to do is go for building a radiation boundary. Okay, so go ahead. Okay, so in this second box, I think that is the radiation boundary. So I go ahead, give this as my radiation box. Okay, material type I have to choose edit and give it as air. Okay, so this is done. Okay, you can give some transparency so that it doesn't obstruct our view of our antenna. Okay, click on apply, you're done. So similarly, the other substrate actually we have done, we haven't named it. So substrate, the material what we are going to use for the substrate is FR4. So FR4 epoxy, click on OK. Okay, so the material is done. Okay, so I think substrate let it be in this color. Apply and click on OK. So we are almost done here. One more thing left is port. So for this, okay, I'll try to find a position in YZ plane. Okay, I'll go for changing the plane. Try to go into this position and fix this. Okay, so this is done. I'm going to label this, change this name as port. Okay, okay, maybe red color I'll do. Okay, so click on OK, apply, done. I have to give the positions properly and dimensions correctly. So I'm taking it from the slide itself. So the position is LF, comma, minus WF by 2, comma, HS. Okay, and for this, I'm taking it as WF and minus H. Yes. Okay. So port is done. So this is almost, we are almost done with the structure now. Okay. So after this, what we have to go and do is, we have to go and assign the radiation boundary properties, the material properties, and then the port things are there. Okay. So to start, I think we can go with selecting the port excitation first. Okay, so we'll go and give the port excitation first. So right click on this and assign excitation, make a lumped port. Okay, next. Okay, here you can give a new line. So join the upper triangle and then your feed is defined now and can finish this part. Okay, so now if you see here in this particular left hand side on the project manager, okay, you can see that feed is correctly placed in that particular position. Okay, so this is done. Okay, so for the radiation box, I think we haven't given the geometry and the position correctly. So I'll give the position, length of the radiation box by 2, comma, width of the radiation box by 2, comma, height of the radiation box by 2. Okay, and then the length of the box, and then the width of the radiation box, and then the height of the radiation box. Okay, so this is done now. Okay. Okay, so this has moved to some other question. Radiation box. Okay, I think I must the minus sign. Now I think it should be able to come into the boundary. All right. So now I've got the antenna fixed within this radiation box. Okay, so with this, we are trying to build the first part of the antenna section. I think we have taken around 20 minutes now. Another 10 minutes, I'll try to take up a simulation and then go ahead. Okay, so this is the blueprint model which we are actually trying to have in our hand. Okay, so with this blueprint model, okay, I have to change up this length and width, okay, and the insert positions, okay, and then I have to try to simulate as much as data as possible for training my ML model. So that's why I first went up with designing the design parameter properties, and then came up with coming up with this model. Okay, so once this is done, okay, I'll save this. Okay, I think still some more things are to be done for this thing. Okay, I have to go into the analysis. Okay, so maybe I'll take this number of processes 10, click on OK, and then for the analysis setup, I have to add the sweeping frequency, make this as fast. Okay, so this is going to be 3 gigahertz, and I'm going to set my step size as 0.01 gigahertz. Okay, and click on OK. So we are done with setting up this thing. Next is getting a rectangular plot of my S11. So S parameter S11 in decibels. Click a new report and close this one. Okay. So this is also done now. So what else? What we have done? Okay. So next is we have assigned the port. We have made the decision boundaries. Radiation boundaries, and then we have given this all these things. But the material is not assigned. So I'll go assign the materials for this. Okay. Right click on this. Go into the assigned boundaries, and then give a perfect E. Click on OK. Okay, and then for the radiation box, for that you have to assign again. You have to go for assigning with the radiation. Okay, click on OK. So if you go into this, you see the radiation boundary set, and then for the antenna also we have given the perfect E radiation boundary. So this is how initially we set up the model. Now save this, okay, and you can try to build n number of replicas of this. Okay, I'm going to save as, okay, maybe I give it as BM1. Okay, save this model. Okay, so this is going to be creating my first model having where did I keep that one? The variations which I have to bring. Okay, so LP, WP, and 0.5 LP by 2. This is my first base model. So for this, I have to find out what is my S11, export the output as Excel file or CSV file. Okay, so for starting with that, to do some modifications in the this thing. So first is take the patch, cut the insert. Okay, and then connect that with the P line. So this is done. Okay, so validate your model. Go into the validation check. Okay, and go and analyze the model. Okay, so this is how you try to build the first one. Next other models you have to keep replicating like this. Okay, so we have done with the simulation, I guess. I think it is going on. Yeah, it's simulating. So I'll wait for some 2 minutes for here. Okay, so this is the usual procedure you can start with. Okay, your casual model you want to bring, put it like everything which could be changed. When I want to do some iterative changes, what variables I have to put. Okay, like here I've taken patch length, patch width, and inserts length. Okay, so this insert length I will try to take first as 0.5 times the half of the patch length, 0.6 times, and then 0.7 times. Like that for 2.4 I will do. Similarly, I will do for 2.5 and then 2.6. Okay, so I think some time for this model itself it is taking. Okay, so I'll wait. Okay, so this is complete. I'll check my result if it is okay. We'll take up. Okay, so you can see that I've designed for 2.4 gigahertz, and my result of S11 what I've got is this one. Okay, so minus 10 dB bandwidth also you would be able to see. What is the frequency sweep at this point also you would be able to see. Okay, so this is how I try to build my base model 1. Okay, so from here I have to try to export this thing. Okay, I'm going to export this as .csv file. I'll open my desktop and I'll try to put this as a FTP. Today is 31st October. Okay, put it, open it. Okay, so this is my base model 1 CSV file. Okay, I put and I'll save it. Okay, so this is done. Okay, now what should I do? I have to go and build my base model 2. For the base model 2, what should be the change? Li should be 0.6 times LP by 2. Okay, so how do I go and do that one is, I have to go open my, this is base model 1. Before this, I have to go and take over my previous model. Okay, what did I start up with? Kits FDP. Okay, open that one. Okay, in that all the other things I have already set. Okay, my port, everything is set. Only thing I have to change is go into the design properties, check this Li. Li I have to change it into, instead of 0.5, I have to make it into 0.6. Before doing this, I have to save this into a separate file. Okay, file save as BM2, my base model 2. Okay, save it. Okay, so I've done the second model now. So into this, go into the design properties, check this Li. Instead of 0.5, I make it as 0.6. Okay, click on OK. Now the dimension is changed. Okay, now come into this model. Yeah, so select this patch and insert, cut them. Okay, subtract them. Okay, so now this cut is done. Okay, now connect that with the feed line. So combination is done. Save it one more time. Okay, and go into HFSS validation check. Okay, go and build my analyze my thing. Okay, so this will take another 2 minutes or so. Okay, so in that time the simulation would be complete for this second base model. Second base model, I have not changed the length and width of the patch. I've just changed my inside length. Okay, so for this, let me check what is the, okay, once this is complete, I'll check what is my return loss, and I'll try to export that also into a separate Excel CSV file. So like this, I'm going to try to do for all the 9 models. Okay, maybe it will take time. I'll try to do for another 1 model and I'll stop with that. Okay, so you can try to do the same thing for the continuation of this. Okay, so for the time being, I'll try to simulate 1 more model and extract the things. So with 3 models, I'll try to build the training target. Yeah, you're done. Okay, so I'll go check this. So I'll check the result here. How is my result? This is pretty much improved in my thing. Okay, maybe if I do the optimization, I may get even more better results. Okay, so I'll try to extract this. Okay, right click on the plot and export. Go into the desktop where name I've given is, okay, so this is my BM2. Okay, so I've extracted that also now. Okay, so what is my next step? I have to go and build my, I have to take my second model. Okay, so for this, file, open, Okay, take my first initial model which I've taken. Open. I'm opening this now. Okay, so I've opened this. The previous model, I'll try to close it out. Okay, so now we are in this base model. I have now here one more liking. Like instead of going with the base model 3, I want to go for base model 4. Okay, let me check with that dimension. So I'll change the LP, WP, and LI also. Okay, so I can give you some understanding how I'm generating this data set. So LP, I'm going to change it into 28.22. Okay, and WP is 36.49. Okay, and LI have to change. So LI is okay. Okay, it's 0.5. Okay. So before I do this change, I have to save this as into another file. Okay, I'll take this as BM3 for my case now for the short explanation. Okay, so I'll do this thing. Come back again, the properties. 28.22, and then WP is taken as 36.49. Okay, and then LI I have to change. Okay, so this is done. Okay, now go with this thing. Okay, patch and insert I have to subtract. Okay, and then add it up, combine it with the thing. Okay, save this one as my third base model. Go validate the model. Okay, and then go and analyze the model. So I think we are real quick now. We should be able to get the results now. So now I have done for 3 models. With this 3 models, we'll try to build our data set. So any structure you have, okay, any structure you have, try to take up little slowly, understand the design, know the metrics on which you want to change. Okay, on changing that, what would be the response? Okay, so that you have to understand. So that you try to take it as an Excel file, bring that out into an ML model, train that, and try to get the best length and width from that. Okay, so the model is still running. Okay, another 1 minute. I'll try to wait and see if this is working. If it is done, I will go immediately into the data set preparation. Okay, done. I think some, okay. Warning is there, but still we'll check whether the results are done. Okay, some results we have got around 2.5, near to that. We have got some minus 10 dB dip. So I'll extract this also. Okay, export this into my desktop. Go into this thing, and this is my base model 3. Okay, so save this file. Okay, so that's all for the HFSS tool, what we are trying to do. Okay, hereafter we are going to work with our Excel only. Okay, so what I'll do, I'll just copy this one file. Okay, and I'll try to label this as my base model data set. Okay, base model data set. Yeah. So open this one. this is going to be the one where I'm going to combine all the three into a single file. Okay, so before doing this one, okay, so check this one. Should not have the square labels in the headings of the column. Okay, headings of the column. So kindly check with that. So first I'll try to insert a few rows. Okay, like a few columns. The first one is for the frequency. Okay, and this is okay, for our easier purpose. Okay, I'll try to have this put in mm. Okay, so this is done. Sorry, frequency in gigahertz. Okay, patch length LP. Okay, in mm. Okay, and patch WP in mm. Okay, and then the insert length. Okay, this is going to be LI. Okay, so like this you have to put. Okay, so as you know, this first one is 29.4. Okay, put this here, and you know what is the width of this thing? So that is 38. So we are manually only putting this one. Okay, and then the length of the section was 0.5, right? So okay, so I think I have to refer this one. Okay, if I go into the model, I may get that one. LI was 7. Okay, not this model, right? Okay. Okay. So anyway, I'll just try to put it 0.5 times LP by 2. Okay, 7.35. So 7.35. So this one you can keep it for the first model. So our first this thing is ready. Okay. So what are the first three columns? These are the input feature vectors for my ML model. This is my target for my ML model. Okay, so this is the features: frequency, patch length, patch width, and insert length. These are the features, and this is the target. Okay, so similarly, I'd go into the other one. Okay, I go into the other one. Okay, go into the second base model. I try to grab out that one out. Okay, so I try to grab this one outside. Okay, and come into the first Excel. Okay, and I give it here. Okay, so this one I have to put it into the last column. Okay, so this is done now. Okay, now but the length and width of the second model, I think this was same. Okay, and the width one was 0.6 times the length of the patch by 2. Okay, length of the patch by 2, that is coming around 8.82. 8.82. Okay, so this is for my second model. Okay, I've done this one. Okay, I've finished this one. Okay, then coming to the third model, I'll try to finish on time. Okay, we'll be trying to finish on time. So this one, I try to come here into my data set, put this back again. Okay, take this one, put this here. Okay, this one, the length is this one. Okay, so I try to put this as my length. My width is 36 point. Because this is the third model I have taken. Okay. Okay, and this one is the insert length. Okay, 7.055. Okay, 7.055. Okay, so this is also done. I have almost done with my preparation of my data set. I have to do some tweaking. I'll show you how I'm tweaking this data set now. Okay, so this is my data set. I may not want to have all the frequencies. I just want to have for the one which S11 is greater than 10. Okay, so that is how I have to go and train my model. Okay, so for that, what I'll do is, okay, I'll save this again as a separate file. Okay, so go back again. Okay, so this is going to be my base model, custom data set. Okay, and click on save. Okay, so go in here. So I've come into the custom, go into the filter section. Okay, so here, okay, so here you can go less than 0.95. Okay. Okay. So now you have got a data set which is rich in values. Okay. So, but I am having only around how much values I've got? Only 22 values I've got. Okay. Maybe this is not sufficient. I'll try to get even more, some 22 values only on the thing. I have to build some more. I've taken only 3 models. So, less than, okay, minus 8 dB I'll fix. Okay, less than minus 8 dB. Okay, I've got again only 27. That's good. Okay, that is also not fine. Okay, so less than minus 7. Okay, I'll not go much than this. Okay, 32 entries have come. So I'll just try to take this alone. Okay. Usually, you should have something around 5,000 rows or more than that, 1,000, 2,000 rows you should have. Okay, so that would be a better model. So first sheet, I'll delete this. So I'm going to have this as my input for my ML model. Okay, I'm just selecting whichever is the best results. Other things I don't want to train my ML model. Okay, so above 7 I've taken, and I've taken this thing. Okay, now is the ML part of this session. Okay, so you can go into your Colab. Okay, you can go open this Colab. Okay, you can. I think you are familiar with this Colab environment. I'll try to put this in the chat also. Okay, you can open this Colab file. Sorry, Colab website. Go into this IDE where you can run the Python codes. Okay, so this is how I'm going to start with the ML modeling. Okay, so go into this. Okay. Okay, so first I'll start with building a okay, XGBoost. I'll try to start with this. Okay. I think I'm little fast, I know, but this recordings, I think ma'am would be able to share over the period of time. And if you can follow this one model link, I think you can try to take it for the other research works what you're doing, be it your reconfigurable antenna. For reconfigurable antenna, there could be more than 40 or 50 parameters, features. Okay, for our simple patch antenna, we have taken just 4 features: frequency, length, width, and the insert length. Okay, if you are trying to work on reconfigurable antennas, there would be so many even more parameters, features, input features, which would be there. Okay, so I'm just going little fast in copying this into this thing. Okay, later section I'll share this with the coordinators. They would be able to give you at the end of the session. Okay, so once I finish putting this into my ML model, I'll try to tell you what each section of this code is describing. Kindly bear with me for another 10 minutes. We'll finish. Mostly we'll try to be on time. You can also, I've taken this XG boost. You can also try with what Jude sir was telling about CNN model or deep belief networks or any ordinary neural networks also. You can try to take it up and you can try for your research purpose. Because very recently people have started, even for some ways or the other, they want to integrate this AI into their work, and that has actually curated more interest among the researchers. Otherwise, there is nothing new into this kind of AI integration. There are CST tools. I think they have an integrated AI also. So this is my version of doing this integration. You can also try with other means. Okay, so I think we have almost come to the final version. Okay. So once you have done this thing, okay, I'm just labeling this file as my okay, XG boost. Okay, YAML model. Okay, I give some name. Okay, click on this side. Okay, it is connecting to this model. Yeah, meanwhile, you can fill the feedback forms. Have a little eye on this section, because this is the prime thing. Okay, you have built the word, that is what to say, you have built this data set now. Okay, we are now going to take this into this collab environment. So for that, to upload that Excel file into this, just click on this upload arrow here, what you can see here. Okay, and go into the folder where you have. Okay. Okay, so I have done the first part. I think I have to give the name correctly here. So base model custom data set. Okay, so this is done. So this one, names of this thing, that will be a little different. I think I have to check this correctly. Most it should be correct only. Yeah, I think rest of the code goes well. Okay, so first part is taking up some libraries which are needed for using some keywords of this particular tool, pandas, numpy, for plotting, matplotlib, and cborn, and for finding out how much time it is taking to train and how much time it is taking to predict. I've used this time label. Okay, and the ML model XG boost also I'm taking up a default model. Okay, in research they try to modify the existing model. You can try that version also. Okay, I'm uploading this Excel file and listing certain first 5 rows of this Excel. Okay, so you can see frequency, patch length, patch width, insert length, and the gain. So the first 4 columns are the features, and the last one is the target. Okay, so I'm going to separate them as features and target. So the columns with frequency, patch length, patch width, and insert length as X, they are the features, and S11, they are the targets, Y. Okay, so I'm doing that one. Some error is there. So yeah, not in the index. Okay. Patch length is not in the index, so I'll check out that one. And some capital mistakes should be there. Okay, this frequency is such. I think it should be working now. We'll check this. So maybe if you get this for code also, you try to check whether how you're able to access this one. Okay, some mistake that is popping out. Showing frequency G is not in the index. It is available. Okay. Okay, I've trained this thing. I've given into some metrics of the model. Okay, and you can see I'm doing the training phase here, and this is for the prediction phase. And at last, printing out the metrics, you can see the R square value is 0.81. It is not up to the mark. Maybe some changes in this model you can do. Okay, maybe make the depth even more. Depth of this is a tree-based regression model. Okay, and the estimators you can also increase, maybe 900 I'll fix. Okay, so do the training again, testing again, see the metrics whether they have done improve. Okay, still not much of change. Okay, why this change is not improving is I have a very limited data set. Okay, that could be one of the reasons why this model is not working. Okay, so that could be one thing. We can improve the number of rows. Okay, as I said, go create some more ML models. Okay, and you can see how the predicted value, actual S11 and predicted value is differing. Okay, it should have closely inclined with this red line if it is correctly matching. But because of some error in this data set model, okay, if you take even more number of samples and put this into training phase, you can very well go and use this. Okay, so this is my presentation for this today's task. As we saw, we started up with the first how the antenna features you can select for different task. Okay, the different metrics of the antenna. Okay, and then we have created in HFSS how to create the base model, and we have seen how to proceed taking up the data set from that. Okay, and then try to build an ML model. What we have tried to do here is XGBoost regression, evaluate their metrics. Okay, and then finally you can optimize also. I'm not covered up in this session because of the time being. I'm skipping this part alone. Okay, you can very well come meet us in the later section through our organizers. Okay, and this is me closing up for now. This is the beautiful scenery near to our campus, the Sirvani Mountains. Okay, and if you have any time, you can meet our campus. And our organizers are doing very good training and research work on this antennas. Okay, you can also reach to me through them. Okay, if any guidance or support needed. I'll be here for another 2 or 3 minutes. If you have any quick queries, you can ask.
Excuse me, sir. Sir,
Yes,
thank you
yes.
for your presentation, sir. Sir, actually, my research is on reconfiguration,
Yes.
sir. Can you give the idea about the
very
list
good.
of features in reconfiguration, sir?
Yeah, very good. I think you can try to incorporate the features of the diode. Okay, the positioning of those diodes and stub related to stubs. You can have a few more length and width configurations. Are you able to see this slide?
Yes, sir.
I think in this slide, if you see in the frequency reconfiguration, okay, these are the basic things. Okay, switchable stub feeds. Okay, the pin diodes, varactors across the slots. Okay, so the structure. Okay, if you are trying to put a slot or if you are trying to introduce a stub, what is the length and width of those stubs? Okay, how many number of stubs are you going to put? Okay, so all those things you can try to make it as an Excel. Okay, put it into after you try to build the model in the HFSS or any other base model, put that into an Excel, extract them as an Excel. Okay, and I have given only one target value here. That is, I have optimized my design only with respect to gain. Okay, maybe in reconfigurable antennas, you would be also needing to improve the gain of the antenna apart from the return loss.
Okay, sir.
Am I right?
Yes, sir.
Yeah, you can try to have another one target column. Okay, so one ML model would be training on the first S11 parameter. Another one ML model would train on the gain of the model.
Okay, sir.
Okay, so this, if you can just work on improving the performance of the surrogate model itself, I think there's a good scope for going for a higher impact applications.
Okay, sir. Okay, sir. So second thing is,
Yeah.
what approach should I go with getting a basic design, sir? Like for any kind of applications, for example, like GPS applications, because there are like a length and width of the patch or substrate is there. So what kind of unique approach can we start to design, sir?
Okay. If you go into Amazon and if you go and see the pricing of a Geo5 or any Wi-Fi modem, okay, there would be some humpty number of modems are there. Okay, but 1 or 2 modems only will be listed in bestseller. Can you tell me why? Both have gone into the design process, but only one of the models would be actually having best selling likes and comments and all those things. Why thing is they have got the design correct, but they have not done the optimization for the user perspective. Okay, so first go with the mathematical design equation. As you can see in our modeling also, first we started with the mathematical expression. Find out the length and width from the EM structure, what you have taken. They have a design equations. Am I correct, Prasanna?
Yes, sir.
Yeah, you have a design equation. Okay, you name the frequency, you name all the other epsilon or all these things. Okay, put that and give it into a design. Okay, and you take out what is length, width, how many stubs, all those things, you can try to put it as an equation, put it as a model in the HFSS. Okay, now you try to simulate and see the results. They would be resonating in the same frequency what you designed, but maybe little different. Okay, but the performance would not be correct. For that, what we will do, we will try to iterate one by one. Okay, we'll try to change the length of a stub or try to increase the number of slots. Okay, so you do a preliminary base model 1, 2, 3 and try to generate all the details in the form of an Excel. Okay, and then come into an ML model like this. Try to do with some deep learning models. I would suggest very recently, deep learning models are very frequently used. Even quantum computing is there in the future. You can try to take up those algorithms. Okay, try to build a surrogate model from them. And then you can go for optimization approach, like genetic algorithm, PSO, particle swarm optimization. Using those models, you can find out what would be the exact geometry or the exact dimensions of your antenna that could yield better S11, better gain. Okay, so start with the math equation, then build the model in the EM simulator, extract those data, analyze them, okay, put that into an ML model, and then you can optimize it further from there. Have I answered you?
Yes, sir.
Yes.
Sir, can we use the ANSYS website resources to get idea about these models, sir? Deep learning models. How to learn, sir? Is there any source, sir? Resources available, sir?
Yeah, ANSYS is also having, MATLAB is also having some toolbox. CST is also having some toolbox. Their website is having some blogs related to customization or optimization. You can refer those things.
Okay, sir. Thank you, sir.
Yeah.
So, excuse me.
Yes.
So if it is a complex geometry, something like you have multiple slots in that, then how do we specify that?
Yeah. So here you can see some. So all those things what you are saying are features of your designed antenna. Am I correct?
Yes,
so slot, you can maybe you can insert one column here. Okay, so slot 1 length. Okay, so I'll put slot 1 width.
from the basic equation, we have to include additional formulas or something like that.
Yeah, or you can first itself go with your randomly. You would have done some model, right?
Yeah.
Only the patch you will go. For the slots, you may not follow the equation.
Yes, yes.
But
yes,
you would have
what
randomly taken some slots, length and width. Okay, that you would have fixed for first model and the second base model and the third base model. Am I correct?
Yes, sir.
Similarly, like that, you can try to generate your data set. Okay, for the slot 2, what is my length? Okay, and for the slot 2, what is my width? Okay, so once you do this for model 1, model 2, and model 3, okay, and you try to generate this S11 value, okay, from there you can try to train up a deep learning model or some ML model, okay, and see which model is performing better. Do a comparison, okay, for your generated model, which one is having a better, convergence between input features and the target values. Okay, as I said, target also need not be only confined to S11. Okay, based on
so
your
that can be done for the reverse processing also, like
inverse modeling also is possible. Very good. Yeah, as I said, you can go with the inverse thing also.
So we have to go for that symmetry equations, and then we go for the design geometry.
Yeah. As you said, like this S11, all the other things you can try to have, and you can find out what should be this thing also. That is also possible. Only thing is you should have a data set for that.
Okay, sir.
Okay. So usually forward modeling is what most of the people try to do. give the dimensions, find out what is the S11
Basic
and
geometry we have to initialize and then we just process it.
yeah.
Instead of optimization, we go for this analysis.
Yeah, this analysis can be done as one part of a paper or something. Okay, try to choose 1 or 2 or 3 models or 4 models, and which model is better converging for the description of your antenna. Okay, the best one would be the surrogate model. Okay, so that model you can try to use it as a one of the element in your optimization algorithm.
Okay.
Okay, optimization part I have not touched up for this session. If you can think about something on that perspective also, it will be useful. Okay, because of time constraint, because I just concentrated giving some inputs on the antenna part, then the ML and the answers part. Okay, so maybe another half an hour if it will take, it will be sufficient, but I don't think it will need it now in this session. Okay, but anyway, you can reach to us, to our coordinators. We can guide you in some way or the other.
Okay, so thank you.
Sir, can you share your contact number and mail ID in the chat box?
Sure, ma'am. Sure, we also have a research program coming up very soon. You can also check with that.
Sir, you can share in chat box.
Okay.
Thank you, sir.
I'll just do this one. All the MIMO antennas, more research. When I started for this, this FDP session, I found many papers on MIMO or the other reconfigurable antennas also are using this surrogate modeling and optimization kind of things. You can refer those things and also get some insights.
Yeah. Sir,
yeah.
Sir, under reconfiguration, you mentioned that there are 49 features are available.
More than 40, yeah.
Yeah, do you have that list, sir? Can you share me if possible, sir?
Yeah, you can reach me out later. I'll share some base papers which are having some related things to that.
Okay, sir. Thank you so much, sir.
Yeah, thank you so much. Yes, ma'am, Shangat ma'am, I think I've taken so much time more.
Thank you very much, sir, for spending your valuable time, valuable information. Hope all participants agree with me. Hope you got a good idea how to integrate AI ML with antenna design.
Thank you so much, ma'am.
Yeah. Thank you.
Thank you for inviting me also into this FTP, ma'am.
So he is one of the experts in our institute who's good in AI ML algorithms, programming. So any help regarding this, you can reach out to Jenkins, sir. Thank you all participants. Hope we will see tomorrow for the last day of our FDP. So tomorrow we are having an industry person from foreign Australia, and he will be telling the importance of wearable antenna, flexible antenna for communication. So tomorrow the session starts at 2:30. 2:30 the session starts, and we are having another session with CST software, how to integrate AI with antenna design in CST software. So thank you all for your active participation. Good night. God bless you. Thank you, sir.
Thank you all. Thank you all. Good night.